Testing. Okay, looks like we're making noise. And so we're going to be talking today about membrane structure. This is pretty important stuff. It's going to connect what we've been talking about in the past with regard to the nature of lipids and proteins to what's coming up next, which is, well, we've already talked about cellular structure and all those membrane-bound organelles we find, especially in eukaryotic cells. And so this is kind of completing the picture for us. Okay? And one piece of the puzzle is this concept of a fluid mosaic, right? So that's kind of a buzzword. Fluid mosaic is the model that we use for membrane structure. Okay? And I guess the questions to address here is, well, what makes a membrane a fluid and what makes it a mosaic? Okay? And so if you don't know what a mosaic is, I'll show you a picture of it relatively soon. But basically, we've got two different parts in a membrane. Right? We've got phospholipids, which form a bilipid layer. Okay? And you already have the idea that there's a phosphate head on one side attached to a glycerol, and also attached to the glycerol, there are two non-polar tails, one of which is unsaturated. There's a little bend in it if you look at the pictures that are there in the textbook. But you've got the hydrophobic portion over here and the hydrophilic portion at the very top. And the hydrophilic portion is the part that interacts with water. The hydrophobic part is excluded by water, so it interacts with other nonpolar parts. We've been through all of that. Okay? And the other thing we find in membranes are proteins, which, as you know at this point, are long chains of amino acids that will form spontaneously coils and sheets and eventually form this three-dimensional protein, three-dimensional globular structure, or some such structures, and in which case one of the forces that holds the protein together in its tertiary shape are interactions between the side chains. And so one thing, we haven't mentioned this before, but we know how nonpolar interactions, how phospholipids interact with other phospholipids by having their phosphate heads together associated with water and their nonpolar tails associated with other nonpolar parts. And so the nonpolar parts are all bunched together in this middle layer. Similarly, in the case of a protein, the nonpolar parts of the protein tend to get bunched together with the other nonpolar parts, right? And so that's a little bit of an elaboration over what we've been talking about so far. But getting back to the original question that we're addressing here, what makes a fluid mosaic? What makes a membrane a fluid mosaic? Well, you've got two different main components, phospholipids and proteins. And the way they come together really does make this fluid mosaic metaphor kind of useful, right? And so if you don't know what a mosaic is, it's a piece of artwork usually where you've got tiles that are set into, that are set on a substrate, then you've got grout around it. It's usually, they're held in place by mortar, but you've got grout in between. And so if you've ever seen a tile wall, you could actually use different colors of tiles to create a picture of something. I'll show you a picture of a mosaic in a little bit. But what I'm saying here is that the tiles in a mosaic are kind of analogous to the proteins, and the mortar or the grout that is in between the tiles is kind of like the phospholipids, right? And that's the mosaic part. It's fluid because there's nothing holding the phospholipids in place, right? Each phospholipid is its own molecule, and it's free to move around relative to the other phospholipids. It's not covalently bonded to other phospholipids. So you have lateral movement of phospholipids relative to each other, right? And so I just want to go back to kind of like a standard diagrammatic picture of a membrane structure where you've got phospholipids, these phosphate head, two tails, and you have the proteins, which are much larger structures, and they tend to have a very specific three-dimensional shape, right? And if you have a side view, the phospholipids are kind of lined up. You might have the outside of the cell over here, the inside of the cell over here, and the protein is held in place largely because you've got nonpolar portions over here that will interact with the nonpolar portions of the phospholipid bilayer, right? So it's like, yeah, the protein has its three-dimensional shape, and moreover, it's actually being held in place in a membrane because the greasier portion of the protein is happily interacting and interacting with the nonpolar portions of the phospholipid, right? And so this is a side view. If you look at it from the top view would basically have the protein here, and the phospholipids would be surrounding it. Like you've got a sea of phospholipids, and like I said, this is a fluid. This is a fluid mortar, and the mortar is kind of shifting around relative to each phospholipid is shifting around relative to each other, and so it is kind of like a tile, a protein tile, that is floating around amidst a sea of independently moving phospholipids. And hence, not just are the phospholipids a fluid, the proteins that are set in the matrix, in the phospholipids, are going to be moving around relative to the other proteins, because really the only thing holding the protein in place is the fact that its nonpolar parts are associated with that nonpolar middle layer of the phospholipids, right? And so the analogy here, and here's where I get to share with you my very favorite mosaic of all time, which is this mosaic of a dog. This is from the ruins in Pompeii, near Naples in Italy. There was the volcano, the Vesuvius volcano, which erupted. I don't remember what year it erupted, maybe 87 BC or something like that. I'm probably wrong about that. I don't do historical years very well, but this is a super cool mosaic. It's on the floor of one of the villas in Pompeii, and basically says "Cave Canem," which basically means "beware of the dog." In other words, it's kind of like a mosaic that's set as you're walking into the house, saying, "Hey, look out! We've got pretty badass dogs around. You don't want to come in here if you're sketchy, right?" And so that's this is a really awesome piece of work. And each individual tile, you can see they're tiny. They're really tiny. You got black tiles and white tiles and gray tiles, but they're all set in a very specific position, and the picture of the dog emerges, right? And so what you want to imagine with a fluid mosaic would be that all the black tiles and the white tiles and gray tiles could move around relative to each other. And so maybe in one moment you might have Cave Canem with a picture of a dog. Maybe the next 5 minutes later you can come back and the tiles have shifted around, and now you're looking at a picture of a cat, and maybe it says Cave Gatem, or however you say "beware of the cat" in Latin, right? Anyways, I mean, I threw this in because maybe not everybody is aware of what a mosaic is, and so there's your bit of cultural enrichment for today, okay? And so, yeah, the fluid mosaic is kind of an important piece in your understanding of how membranes work. It is the structure of, you take the mass of a membrane, there's actually more protein by mass than phospholipid, but not by a lot. It's about 60% protein and 40% phospholipid in a typical animal cell membrane, right? And proteins are pretty massive, and sometimes they're really huge. And so it's not too surprising to me that the tiles in this fluid mosaic are actually more massive than the mortar and the grout in which they're set. Okay, so that's one item for discussion done, right? The second item for discussion has to deal with the permeability properties. And here I only want you to think of the phospholipid bilayer, the bilipid membrane. Okay? So bilayer. So you can see that each one of these molecules is our phospholipid bilayer, and it spontaneously forms. Okay, in water. Okay? And this is kind of an important point for a couple of reasons. One, we don't have to have any any cellular mechanism creating a phospholipid bilayer. Now, all we need to do is create the phospholipids, and it spontaneously forms a membrane-like structure, a bilayer-like structure, because of the presence of water. Okay? And the reason why it forms this bilayer is because this is one of the stable structures where you've got the phosphate heads interacting with water molecules on the outside. Water molecules are all outside the cell. Water molecules are inside the cell. And this is a way in which we could have the water molecules interacting happily with the phosphate heads, but not interacting with the tails that are in between. This middle layer in between is kind of greasy, and there's not a whole lot of water in between in that middle layer because water molecules like to interact with other polar things, right? And that's, again, kind of like a review of where you've been. The other thing about this is that even though we've got this nonpolar middle layer, it's actually permeable to water molecules. Water molecules are small enough to pass through. Okay. Why do they pass through? Well, the phospholipid molecules are big compared to water molecules. And as they're shifting around, sometimes you get a little gap, right? So maybe these things are shifting around and you'll have a little gap that opens up right through here, right? A little gap right through here, right? That opens up for a moment, and as that gap is open, a water molecule, undo that. The water molecule can zip through. A water molecule zips through, and so it is over here. Maybe another water molecule over here is going to zip through in the other direction. It'll end up on the inside of the membrane, right? So water molecules are able to pass through the phospholipids, not because they like interacting with the nonpolar middle layer, okay, but because these phospholipids are moving around, and as a result, these small gaps are opening up in the phospholipid bilayer, and that allows water molecules to move through. They're simply small enough to pass through, even though there's nothing about the water molecule that wants to interact with the middle layer, right? If you are nonpolar, if you are a nonpolar substance, okay. A couple of examples here. Oxygen, O2, O double bonded with O. Okay, you might say, well, yeah, O is very electronegative, and so these are pulling electrons pretty hard. But because we have equal pools on both sides of these covalent bonds, there's no net charge difference between either side of the bond, and so this would be a nonpolar molecule. Okay. And so an oxygen molecule being nonpolar, if it's in solution in water, it can basically move right through the membrane because it doesn't mind being in that nonpolar middle layer. In fact, it kind of likes being there, but it moves through anyways, right? CO2 is another, this is a weird one. CO2, it's a carbon molecule with two oxygens attached to it. And you might say, well, oxygen must be pulling on the electrons harder than the carbon. But that doesn't matter because it's like the carbon is here in the middle, but you've got oxygens pulling over here, oxygen pulling over here, and they're pulling symmetrically. So we don't end up with any net charge anywhere in the molecule. This is another nonpolar molecule. Okay, and so CO2 molecule on this side would be able to freely diffuse across, right? And you also have substances like a steroid. Remember, steroids are in the lipid class. They've got a 4-ring structure. Don't remember exactly what it looks like. There's the D ring has got 5 members, and sometimes it's got little hydrocarbon chains on it. A steroid molecule is nonpolar. And even though it's relatively large, because it's large, it can pass through relatively easily, right? And here the key feature is that you can pass through a phospholipid bilayer, A, if you're small enough to make it through, or B, if you are nonpolar and thereby not excluded by that nonpolar middle layer, right? Things that can't pass through, okay, are things that tend to be large and polar, right? Or charged, right? Like ions. Right? Sodium ion is, even though it's relatively small, it's got a charge on it. And so water molecules are surrounding it like a bunch of little groupies. Water molecules are forming this shell around a sodium ion. And because of the presence of all these water molecules sitting around like little groupies, the whole structure, the sodium ion plus all of its surrounding water molecules, is too large to pass through the gaps that are there in the like this one here in the phospholipid bilayer. Larger polar molecules like glucose, C6H12O6, simply too big. It's not going to be able to pass through the phospholipid bilayer. And so you've got some solutes that are able to permeate and some solutes that are not able to permeate. Okay. And so I think that's covering the things that I needed to cover in this portion. We talked about the bilipid permeability to water, bilipid, the phospholipid bilayer permeable to nonpolar solutes, and the fact that the polar solutes as well as the charged ions are entities that will not pass through the phospholipid bilayer, right? We'll just kind of briefly mention this. We'll see it discussed in the chapters that we'll be scrolling through next. And it has to deal with the origin of life. I mean, basically, life originated roughly 3.6 billion years ago. And we have evidence from the fossil record of smudges on the Earth that are pretty clearly cellular. And so the fact that we have cells 3.6 billion years ago begs the question of how did those first cells arise from nothingness, right? And so here, it's really kind of like a fundamental philosophical question. What would you have if you don't have a membrane? And the answer is, well, not a cell, because a cell is kind of by definition this entity that is defined as something distinct from the rest of the world by the plasma membrane, right? So the reason why we can identify what's inside the cell and outside the cell, what constitutes something that's intracellular versus something that's extracellular, well, the plasma membrane defines that, right? And so I think one point here is that, well, the origin of cellular life had to require, at the very least, some type of membrane that defined where the cell began and where the outside of the cell began, right? And so when you look at cellular origin stories, like what people will be thinking about a lot as the information comes back from the Perseverance rover that's on Mars, it's exploring the Jezero crater, in large part to investigate weather conditions in the early Martian existence atmosphere might have also been conducive to the origin of life as it was on Earth. Okay? And so big questions like how did cells originate are going to have to involve some understanding of the origin of membranes. Okay? And to that extent, it's actually pretty easy because phospholipids are not terribly difficult to envision getting synthesized. You have to have a mechanism to generate fatty acids. You have to have a mechanism to put fatty acids together with phosphate groups. But the synthesis of phospholipids is all you have to account for in order to generate cellular membranes, or at least something resembling a cellular membrane closely enough to allow for us to be talking about the origin of cells. Okay. So let's move on to our textbook scroll through. Okay. Come back here. It's not the thing that I wanted to talk about. Oh, membranes are fluids. Yeah, so this basically is a more fancy picture of what we were talking about before. You've got the phospholipid bilayer here. It's not really showing you the overwhelming abundance of proteins in a phospholipid, in a typical cellular membrane, but it does show you the sea of phospholipids and the proteins that are studded as little tiles inside of the fluid grout, right? And so there's also a nice little video that will, I can't show the video to you on a YouTube because I'd be violating all kinds of copyright laws. But if you have access to it, this particular video is kind of nice, right? If you don't have access to it, hey, no big deal. I mean, it would be nice for me to be able to share that with you. Maybe you can get somebody to find out a way of how they could share that with you on a Zoom meeting. Oops. Okay, so 5.2, we briefly discussed this and said, well, yeah, if we have a mechanism to generate phospholipids, you can get these water-filled bubbles made of phospholipids, and that's not a cell yet either. I mean, just because we've got a phospholipid bilayer does not make it a cell. You have to have lots of stuff inside, metabolizing and replicating molecules, and that's another story that I'll be happy to talk with you about. All you have to do is take my BIO110 class, right? This class, we're going to be moving into the next portion of the discussion, which has to deal with another concept. And it's basically coming down to two things, gradients and two phenomena, one being diffusion and one being equilibrium, or one being diffusion and the other one being osmosis, right? And so I'm going to return back to my whiteboard because I kind of like having whiteboard share so I can kind of draw things out for you, maybe talk to you about what's going on. I'll actually keep this in place, right? No, I'm not going to do that. I'm going to create a whole new diagram, which is to say that you've got two processes going on, one being diffusion. These are key concepts, another being osmosis. Before we get there, I want to discuss two terms for you, one being gradient. Okay. Maybe some of you are familiar with it. Gradient versus the absence of a gradient, and we'll call that equilibrium. Okay. And this is where I want to start out. Okay. So a gradient means you've got differences. Okay. Whereas equilibrium, you basically have no differences. Things are equal. So it's actually, if you think of equilibrium being things are equal, differences being the contrasting situation. If you don't have equilibrium, things aren't equal, then you've got some type of gradient. Okay. Good example might be you could have a temperature gradient. Okay. You open the fridge, it's a summer day, the room, because you don't have air conditioning, is 26 degrees, right? That's Celsius, it's a pretty warm room. Comfortable room temperature is around 20, 21. So 26 degrees Celsius would be an uncomfortably warm room. You open the fridge, and inside the fridge, it's around 4 degrees, right? So fridge, room, there's a gradient, right? Now, what's going to happen if you leave the fridge open, or let's say the fridge is going to turn itself off after its energy. If you leave the fridge open, it'll try to fight it for a while, and then eventually it'll turn itself off, right? If you leave the fridge open and you don't have any more juice running to the fridge, eventually we'll come to a temperature, an equilibrium temperature. Maybe the fridge will cool off the room to maybe 24 degrees, and the fridge will warm up to the point where it matches the temperature inside the room, right? Okay, so what I'm saying here is that this is a gradient because you've got differences. Whereas when you reach the point where you've got equal temperatures throughout the room, including the open fridge, that would be equilibrium. Okay. And the other thing that's notable here is that the pathway, starting out with a gradient and moving towards an equilibrium, is something that happens spontaneously and in a natural way. It's like the universe wants us to reach the point where you've got equal temperatures throughout the entire room and the open fridge, right? You would never say, okay, well, I'm going to open this box and it's 24 degrees and all the cold will go into the box and the room will be left a little bit warmer, right? If you were to have this situation, you would never expect the natural universe to take you back to the place where you started out, where the inside of the fridge is 4 degrees and the outside of the fridge is 26 degrees, right? So it's like the direction always goes from a gradient towards the equilibrium, and that's kind of like what the universe does. It's kind of like a natural law of the universe, right? It's what happens without any help. Okay, good with that? Now, another kind of gradient would be a concentration gradient. Right? Because if you were to have an aquarium filled with water, no fish, because you're going to be adding solids to it. So you had water in the aquarium, and you were to pour in blue dye. I'll make it red dye because I've already made everything red here, right? Blue here. So you pour in red dye on this side, so that the left-hand side of the aquarium it's got a lot of red color. This would be a high concentration. Okay. Whereas the concentration of red dye over here would be low, right? This would be a gradient. What's going to happen over time? Well, we would see the gradient dissipate, okay? And you would end up with an aquarium in which the red dye was uniformly spread out throughout the entire aquarium, and you wouldn't have any differences at all, right? It's supposed to be uniformly pink, right? Equilibrium. With me on that? I mean, there's a directionality to the way things move through the laws of nature. You never see the opposite forming happening, right? You could start out with an aquarium full of pink water. Would you ever expect all the pink particles to move all the way over to the left-hand side of the aquarium like you had initially here? No, that's not going to happen, right? There's a directionality, and this is basically one of the laws of the universe. It's one of the laws of thermodynamics. We're not going to get into that kind of detail here, but the concept of gradient and equilibrium is a really important starting point. Okay? Nature always wants to push us towards the equilibrium, where you've got equal things throughout the entire system. Okay? And having said that, you can imagine now a situation where you've got a membrane. In fact, I can go back to my share of the textbook, right? And so here we're looking at exactly that same situation. Annotate, draw. Okay. Here you've got high concentration on the left-hand side, a low concentration on the right-hand side. And what we have in the middle is the membrane. The pores are large enough for the molecules of dye to move through. At the end, we've got equilibrium. Because the particles have moved to a state in which you've got the situation. That's that state of equilibrium. Things are equal throughout the entire system, right? Moreover, it can happen in both directions. It can happen both ways. You could have a gradient of maybe high concentration of sugar on one side, high concentration of salt on the other side, right? Here's purple over here. Oops, nope, don't want to do that. High concentration of salt on the right side, a low concentration of salt on the left side. And what happens is that we're basically moving towards a double equilibrium where we've got equal concentrations of sugar and salt on both sides, right? And so, well, and in this case, while the salt molecules are moving from right to left, the overall situation is always moving from gradient, right? The existence of a gradient to the absence of a gradient, which is what we're calling equilibrium. Okay? That settled for you? Okay, and so the idea of this is that the diffusion starts out with some type of concentration gradient. We've got a gradient of solutes. This might be sugar. Diffusion is going to be the movement of solutes in a direction that takes us to equilibrium. Solute 2, we've got a concentration gradient of salt with high on the right side, low on the left side, and it's moving towards an equilibrium where we don't have a gradient at all, right? So equilibrium is a state where you've got equal concentrations throughout. And that's diffusion. Now, when we move over into the discussion of osmosis, okay, we need to take into consideration the fact that the sugar and the salt here are sitting in the middle of this material over here, which is entirely water, right? Bazillions and bazillions of water molecules on both sides of the membrane. Okay. What would happen if, and the other thing is that the membrane is permeable to water. What would happen if the membrane were not permeable to the solutes? And here's where you get to the next section. Okay. So when we talk about osmosis, we're typically thinking about the situation where the solute particles, pick something here, the solute particles are too big to pass through. This is a non-permeating solute. Okay. And so we've got a high concentration of the solute on the right-hand side, a low concentration on the left-hand side. Okay. The direction of diffusion would be for the molecules of solute to go from the right to the left. Okay. That doesn't happen because the pores don't allow the solutes through. Okay. Equilibrium is going to take place when we've got equal concentrations on both sides. Right? And so we know that the molecules of solute can't go from right to left. one way that equilibrium can be reached is for the water molecules to move in this direction from left to right, right? In other words, if we were to take water molecules out from the left side of the system and bring them over to the right side of the system, we would be diluting the solutes, the sugars, on the right-hand side so that we would ultimately get to an equilibrium with an equal concentration on both sides of the membrane. Okay. So I'll play that back if you need to, but the idea here is osmosis is the movement of solvent. Okay. And it's happening typically in the opposite direction of the diffusion gradient. I mean, the concentration gradient of the solutes would predict that the solute molecule is going to be moving from the high concentration to low concentration, right? Water is going to be doing the opposite because water is there's a greater abundance of water on the right-hand side, high water. Okay. Relatively speaking, a lower concentration of water on the right-hand side. Water is basically moving from where it's abundant to where it is less abundant. So we would actually have water moving in the opposite direction through osmosis. Okay. Now, one way that this plays out significantly for you guys as you'll be moving into a class like physiology will be where you think about, well, what constitutes osmotic equilibrium for cells, right? Like osmotic equilibrium. Okay. Osmotic equilibrium happens when the movement of water into the cell and movement of water out of the cell is equally balanced, right? If you were to have exosmosis, water out greater than water in, you would basically have the cells shriveling up and getting potentially dehydrated, right? If we had endosmosis, water in greater than water out, we're putting cells under a different form of osmotic stress. We're basically getting water molecules to flow in to the point where the pressure inside gets so great in the plasma membrane is disrupted, eventually lysing and killing the cell, right? You can actually see this. You'll probably be doing a lab with red blood cells when you take physiology, where you'll put cells, red blood cells in different concentrations of either sucrose or glucose or sodium chloride, and you'll see how, yeah, those cells are perfectly happy if they're in isotonic saline, right? But if you put them in a saline solution that's too salty, they tend to shrivel. If you put them in a saline solution that is too not salty enough, they tend to swell up. And if it's fresh enough to a certain point, it's actually going to lyse and pop, right? And so, the reason why you need to store your contact lenses in isotonic saline is because those contact lenses are going to be put against your eyes, and the cells in your eyes don't want to be disrupted either by osmotic stress in a hypotonic solution or osmotic stress in a hypertonic solution. And we keep our eyes comfortable by having them always in contact with isotonic solutions. Right. I think that, oh no, there is one more thing that I do need to address. And I'm going to go back to my whiteboard share for this. Okay, not that one. All right. Now, I will see if I can erase some of this stuff. You know those proteins that we were talking about before with the fluid mosaic? Um, one of the things they do is to create like a little channel. In other words, there's a little channel here. That might allow something in particular. I mean, it's a very specific channel. It's not going to let anything through. It's not just like a big old hole. It's something that will allow something to pass through, even though it would not normally pass through the phospholipid bilayer, right? So maybe this particular channel is going to be allowing the passage of sodium ion, right? Sodium ion over here in a high concentration. Sodium ion over here is going to be there, but maybe in a very low concentration. The sodium ion from the right-hand side is going to be able to attach to the ion channel, and it will be allowed through an A+, right? So this is actually using that concept of diffusion in the context of an actual membrane. Okay? Now here's the thing, right? High concentration on the right, low concentration on the left. The movement from right to left is going to be moving in the same direction. Or sometimes we'll use the same direction concept or verbiage, or with the concentration gradient. Right? We're basically allowing the sodium molecules to move, the sodium ions to move in the direction that they would be moving spontaneously in the absence of the membrane. Okay? And so if we do this, we're basically allowing the natural universe, the natural forces of the universe, to move towards an equilibrium state. Okay? In other words, it's spontaneous and it requires no outside energy. And in fact, there's energy that is released because we start off with greater energy potential and end up with less potential. But the fact that there's no energy required means that this is going to be an exergonic reaction. Okay? You just say, whether it's exergonic or not, we're not always going to be making use of the energy that's released. But at the very least, you'll realize that there's no requirement of ATP energy. Okay? Because in the next lecture, we'll be talking about how sometimes we actually need to move things, large, polar, or charged solutes, from a side which we've got low concentrations. I mean, hypothetically, if we needed to take sodium ions from the left-hand side and move them over to the right, okay, this process would require energy. Because it's going in the opposite direction or against the gradient. Okay? And so, again, we are moving, the purpose here, we're moving in the direction of understanding why some types of movement of solutes through protein channels happens for free, not requiring any ATP, while other kinds of movement of ions and solutes across a membrane is going to be actively requiring the consumption of ATP energy. Okay, let me go back to my whiteboard now. The original picture, cutting out our discussion. I did kind of skip this one. Let's make sure I cover that. Osmotic gradient. They're both driven by concentration gradients. That's not a typo. Okay. Diffusion and osmosis are kind of like opposite sides of the same coin that are based on starting out with a concentration gradient and moving in a direction, allowing the natural universe to move in a direction towards that state of osmotic equilibrium / diffusion equilibrium. Okay. I didn't talk about pressure gradients. The example that I actually ended up using was a temperature gradient. I'll be happy to do that in our live meeting if you need to. The membrane proteins, we did talk about that. Membrane proteins, which are the tiles in our fluid mosaic, can be these channels which will facilitate diffusion. They don't require any outside energy, and therefore facilitated diffusion of solutes is going to be an exergonic process. And I did note that the other process going in the opposite direction would be endergonic. Right? And yeah, I did throw in a plug for the video structure and function of plasma membranes, if you have it available. Okay? I'm thinking that some of you are using the e-text, in which case you'll have available the access to the little instructional videos. Okay. Now, the one thing I wanted to go through is I didn't really, I mentioned this, but the idea is that if you start out with, if you start out with a gradient and you move towards an equilibrium, right? This happens spontaneously. The original status with the gradient, okay, that is, there is potential energy. Okay. Potential energy higher. Okay. No gradient. Okay. There's nothing more you can do with that. Once you've reached diffusion equilibrium and the solutes are uniformly dispersed throughout the entire system, you can't make it go in the opposite direction, right? Well, you could say we could theoretically harness the energy of this concentration gradient, and maybe have the particles of dye drive a little machine as they're moving in a net direction towards equilibrium. We can't really do the same thing going in the opposite direction. So equilibrium represents no or less potential energy. Another example would be if you had water in a lake over here, and you had a river that was flowing from a bottom release dam. The energy potential is over here. Water in this lake over here is going to have energy potential. By the time the water gets to the lowest point, there's going to be less energy available for that. And you could use that energy potential to turn turbines to generate electrical energy for the grid. Okay? And so, yeah, I just, not a hugely important point, but I did have it in my outline. And it does kind of fit in with the idea that when things move with the gradient, we're actually releasing energy, and we don't need to have any energy coming in. Go in the opposite direction, you would have to put energy in. Okay, that's it. I will see you in the next video, and I think this one is going to be a little bit longer than, this video was longer than our typical one.